Hi everyone, up to the last lecture, we have learned how to use the G device. For remaining lectures, some examples are considered. The first example is the Dynamic Random Access Memory DRAM. The DRAM has several cells in it. First, the cell structure is introduced. The DRAM cell has one transistor and one capacitor. Voltages of the bit line and the word line can be applied. The capacitor voltage represents data. Since it has a very simple structure, we can reduce its area. It is directly related with the cost effectiveness. Since the small area is important, actually, non-planar devices are used as cell transistors. In those devices, we have long effective channels. However, in this example, we just use a simple planar MOSFET only for simplicity. Its parameters are shown here and the IV characteristics are drawn in this graph. A capacitor is said to be 30 femtofarad in this example. Then, how can you write 0 or 1 to the capacitor? What we want to do is to change the capacitor voltage. When we write 0, we wanted to make it close to 0 volt. On the other hand, when we write 1, we wanted to make it close to VDD. Depending on the data value, the bit line voltage is selected. When we want to write 0, the bit line voltage is 0. When you want to write 1, VDD is applied. In this graph, we show the situation to write 1. Also, the word line is highly biased. Then the capacitor voltage follows the bit line voltage. When you write 1, the capacitor voltage cannot increase up to VDD. Its maximum value is limited to VDD minus VTH because the MOSFET is then turned off. How can you read the data stored in the capacitor? In this time, the bit line is plotted. Depending on the capacitor voltage, the bit line voltage is slightly changed when the word line is raised. We must consider the capacitance of the bit line. When we consider the write operation, we didn't consider it because the bit line voltage was applied. However, during the read operation, it must be included. Typically, the bit line capacitance is much larger than the cell capacitance C sub S. It is noted that the bit line is pre-charged to the half VDD before it is floated. Therefore, the total charge in the bit line and the capacitor can be written as this form. Two capacitors have different voltages. When the word line is raised, the total charge is shared by two capacitors. then the shared voltage becomes this form. The change of the bin-line voltage is simply given as this form. The difference between the data voltage and the pre-charge voltage. It is multiplied by this factor Cs over CVL plus C sub S. Since the bin-line capacitance C sub VL is much larger than C sub S, this ratio is not that high. Only a small voltage change can be made. Then this small voltage change is amplified by the sense amplifier. The retention of a memory means an ability to keep the written data even after a long time. For a non-volatile memory, such as a NAND flash memory, typical retention time will be years. When the electric power is supplied, the SRAM, static random access memory, can retain the written data. However, for the DRAM cell, even when the electric power is supplied, the retention time is quite short. After we write 1, the capacitor voltage should be close to VDD. Even after a long time, its value should be kept. This figure shows the 100 nanosecond long transient result. How does it look like? Can you recognize any change? Probably not. However, it is reminded that the data node is connected not only to the capacitor but also to the MOSFET. Of course, the gate of the MOSFET word line is biased to 0. Even in this condition, we may have a small leakage current. The channel leakage may exist. Also, the junction leakage may contribute. These leakage currents introduce the reduction of capacitor voltage. Is it really observed in our example? This figure just shows the same transient simulation result. However, it is much magnified. Actually, the y-axis variable voltage has an extremely narrow range, 0.2 nanovolt. As you can see, during 90 nanoseconds, about 4 or 5 times 10 to the minus 11 volt is reduced. Quite small. Yes, during 90 seconds, nothing happens. Then, how about 1 second later? With a linear extrapolation, the reduction will be about 0.4 millivolt, still small. Then, after 10 seconds, after 100 seconds, after 1000 seconds, well, eventually, the stored data will be lost. Once after the data is lost, the read operation will have a result of 0. We have data failure. In order to prevent the data failure, we must refresh each cell often. For refresh, we must read the data and rewrite it. Therefore, the DRAM continuously consumes the electric power. Okay, That's it for this lecture 18. In this lecture, we have considered a DRAM cell. In the next lecture, a multi-gate transistor will be considered. Also, the quantum effect inside a multi-gate transistor will be discussed. Thank you and see you later.